And we observed in the previous class that what is lexical analysis, what is lexical analyzer, how lexical analyzer works, and how lexical analyzer communicate with the syntax analyzer or parser, and how lexical analyzer is responsible for generating the tokens. What is pattern? What is token? What is lexemes? There are differences between them. We have vividly discussed in the first part of the lexical analysis. Now, in this section or in this particular class, we are going to discuss about the second part of the lexical analysis. Our objective is to finish the lexical analysis chapter or module within the next Wednesday, so that we can able to concentrate on, concentrate on the next module, that is intermediate code generation, which is from my part. So without wasting further time, I move to that particular section. But before that, I would like to advise you to please reply me whether you are properly audible or not. Are you audible? You can
Yes,
unmute.
sir. Yes,
Yes,
sir.
sir, audible. And
So I am audible. So I am also sharing my attendance screens. Normally I do that at the beginning of my lecture hours. Okay. So I have basically shared my attendance link. Okay. If any one of you asks me any questions, you can able to unmute yourself and ask any question to me. You can stop me at any point of time in between my our lecture session, and you are free to ask questions. Even if your questions is silly, I will very much appreciate that you should participate and join in the question answer session, because otherwise the lecture will be monotonous and boring. Okay, so let me share my screen. I hope my computer screen is visible to everyone. I stop my video and I go to the PowerPoint presentation mode. I hope my computer screen is visible to all of you.
yes, sir, visible.
So this is my basically this is my second lecture regarding the lexical analysis, and previous lecture we have observed that what is token. Okay, what is the different types of, what are the different operations of lexical analysis we have observed, which are recognizing tokens and ignore white spaces or comments, which we have observed by means of a C programming. Error reporting, such as syntactical errors or syntactical error reporting is one of the major part of lexical analysis. Then model using the regular expression and recognize the finite state automata. Next is that the lexical, we are going to observe in case of the lexical analysis, what is basically the token and what are the different categories of it. The different categories of it may be number, identified, keyword, or string. Sequence of character, what is lexemes? Sequence of characters in a token is called lexemes, and lexemes are basically, suppose example 100.01 is a lexeme, counter, constant, const. This is also a lexeme. How are you? Question mark. This is a lexeme. Rules of description is a pattern. For example, if I write a, within double bracket a b star, then it becomes a particular rule or pattern through which you can generate I can generate basically the different types of strings. So this is particular rule, so it is known as pattern. Task identify token. What is the task of the lexical analysis? To identify the tokens and the corresponding lexemes. Our task is to identify the tokens and the corresponding lexemes. That is my task. Then I have discussed that what is how to construct the constants, how to construct the constants in case of the lexical analysis. In order to construct the constants of the lexical analysis, first of all, the number needs to be converted to token number or identifier. Then the token identifier must have an attribute value which need to be written by separated by comma. For example, say 31. 31 is basically a number that we are representing. When we are representing by means of a token, by means of a token, then within angular bracket I have to write that num comma 31. So 31 is basically a constant which we are converting into the token like this, okay. Similarly, if we have an identifier, say id equal to id plus id, then we can able to generate the tokens as id comma 1 within angular brackets equal to within angular brackets id comma 2 within angular brackets plus within angular brackets and id comma 3 within angular brackets. And we first of all need to check that whether that id or identifier is a keyword or not. If not keyword, then we can able to represent it in this way. We need to discard whatever does not contribute to parsing. That means in case of the parser, the blank space, tabs and new lines or comments are not required, so we need to delete all these, okay. So here in this case, we are observing with the help of this block diagram that how lexical analyzer is requesting the user or requesting the computer or the source program to read the characters. So and then the source program to basically sends one line of code to the lexical analyzer. And lexical analyzer is basically generates the token, and that token is basically and that token is transmitted to the syntax analyzer. Whenever syntax analyzer basically generates the parse tree and syntax analyzer has nothing else to do, it then asks for the next token to the lexical analyzer. So after getting the responses of the syntax analyzer, lexical analyzer will request the computer or the source program to send the next piece of code or next line of code, okay. Now we need to find it out that what are the approaches to implementations, okay. uh, Basically the what are the approaches to implementations. If you talk about the computer understandable language, then we know that there are basically three types of languages. First one is basically the high level language. The first and top level language is the high level language like C. But high level language is very efficient, very easily understandable to the user, but high level language is very difficult to implement by the computer internal hardware components of the computer. We already know that because the hardware level basically understands the zero ones combinations or binary numbers, but high level language does not represents the high level numbers. So high level language must be need to be converted to the mm, binary numbers first, then we can able to implement it. So that is why it is very difficult to implement. And for this high level to assembly level to low level or machine level conversion requires a lots of time and lots of time. So the cost is very high and it is also time consuming. And so, but in case of the assembly language, we observe that it is most efficient and but most difficult to implement. Uh, Difficult to implement. It is very difficult to implement because we require some assemblers particularly. That is why it is difficult to implement, but it is most efficient because directly the machine level language can be generated from the assembly level language. Directly the machine level language can be generated from the assembly level language. For example, I can give an example which you can able to observe. For example, say LDA 7050, okay, then HLT. Very easily it can be implemented. How it can be implemented? Suppose I have started storing the opcode or the operand from 8000 memory locations. So LDA is 32. Okay, next is 8001 will contain 50, 8002 will contain 70. Halt halt opcode is 76, which is stored in 8003. Now 32 is basically the assembly code. So 32 can easily be converted into the binary code. Okay, very easily. Now 50 is basically the assembly code and it can easily be converted into the binary code. And 72 is an assembly 70 is an assembly code. It can be easily converted to binary code, and 76 also. So how 32 is basically converted? Very simple to understand. That 32 is segregated into 2 parts, 3 and 2. So we are going to observe that this is basically converted as 0011, then 0010. This is how 32 can be represented. Next is 50. 50 can be represented in this way. First is 5. We represent it by 4 bits, 00101, and then 0000 for 0. Then is 70. So 77 is represented by 0111, that is 7, and for 0, this is 0000, and 76 can be represented by 0111, and 6 can be represented by 100. Now look at that, how easily this machine code or binary codes has been generated. So that is why I am saying that it is most efficient, but it is very difficult to implement, because first of all, because we have to write our code in assembly level language. Most of the user does not know assembly level languages. For implementation of the assembly level language, we require the assembler or particular microprocessor. Assembly codes are basically microprocessor specific, whereas high level language are not microprocessor specific. Okay, so this is the case. So that is why the solution is easy tools like Lex or Flex. So easy implement, but not as efficient as fast two cases. So that is why we are using the Lex or Flex. Okay, for this kind of conversions from high level language to low level language and low level language to high level language conversion. The next one is the symbol table. Symbol table has already been discussed earlier. So what is symbols table? First of all, it stores information for subsequent phases. Okay, interface to symbol table. First of all, insert S comma T. If I write this kind of thing, then it indicates that we are saving the lexing S and token T and returned a pointer to my computer. Okay, so and lookup is, you are already basically accustomed with the lookup concept. Return index, what is lookup is, it will return the index of entry for lexing x, or 0 if x is not found. So where the basically entry of S is present in the symbol table, lookup will return that particular basically entry or index number. If X is situated at 01 position, then that entry or index number will be returned by the lookup function. And if the s is not at all present in the lookup symbol table, then lookup function will return 0. Okay, I hope that this point is properly understood. Whenever we are inserting, we have to insert is basically, what is insert? Insert is basically a function. Insert requires two arguments. First argument is s, which is basically the lexeme. Second argument is the token. That means from where basically the lexeme is being the token t, from where the lexemes is basically taken. So symbols table stored informations of the subsequent phases, that we understood from this point. Implementation of the symbol table, fixed amount of space to store lexemes. Fixed amount of space to store lexeme. It is absolutely not advisable, as because there is a waste of space. If I fixed that I need suppose 1 MB space for storing my lexemes, and I have used only say 200 kilobyte of spaces out of 1 MB space, then naturally rest of the space is completely been waste. So fixed amount of space for storing lexeme, this concept is absolutely not advisable. It should be a dynamic. The storing amount of space required for storing the lexeme should be dynamic in nature. Store lexemes in a separate array. So we are each lexemes is separated by EOS, or end of S, or end of lexemes, separated by symbol end of lexeme. Symbol table has pointers to lexemes. So every lexemes has a particular pointer through which the basically the computer or compiler can able to track which lexemes we are basically accessing. So lexemes are basically stored in a separate array. For example, we are observing that basically two types of lexemes operations, where we are observing that fixed space for lexemes are present there, so which is nothing but the wastage of space. And then we are observing that dynamic allocations of the lexemes in the second case, where the symbol table is divided into two sections. First section is basically the pointer to the lexeme, then and the second section is the other attribute, usually 4 bytes. Okay, so this particular attribute, what happens in that case is that there is a pointer associated with that, and this pointer will leads to us to the lexemes 1, and each lexemes will end it up with the help end it up with the help of the particular symbol end of lexeme. For example, every string is basically ended with the help of the null characters. Just in the same way, every lexeme is ended up with the help of the end of the string or end of the lexeme symbol. S stands for string or lexemes. You please try to understand that. So this pointer is leading me to the first lexeme. Similarly, this pointer will leads me to the second lexeme. Similarly, this pointer will leads me to the third lexeme. Similarly, this pointer will leads me to the fourth lexeme. Okay, in case of the other attributes, we can able to put some other attribute values. For example, say num comma one. So one we can able to put over there. So if there is a lexeme, then we are going to allocate time memory dynamically in the symbol table. Otherwise, we are going to this particular symbol table will be absolutely free. Okay, so there is a much less wastage of memory in case of the dynamically created lexeme. So this may be a very important question. What is the differences between statically created lexemes and dynamically created lexeme? Normally in statically created lexeme, there is a fixed byte. For example, say 32 bytes is always fixed for storing the lexemes. And in case of the dynamically created symbol table, we observe that 4 bytes is usually used. 4 bytes is usually used. Next, we are observe how to handle basically the keywords. Keywords, so consider this kind of token div and mod. Okay, so div is represented by the lexeme small div and mod is represented by the lexeme mod. Okay, can anybody tell me what div stands for and what mod stands for? Can anybody tell me that why div is what div stands for and what mov stands for? Aditi, can you tell me what div stands for? Aditi Ghosh, section G, roll number 3.
Sir, can I tell?
Yes, please, Moinak.
Sir, DIV stands for division.
Division. So div is written in which language? High level language or assembly level language?
Sir, DIV is written in assembly level language.
Okay, fine. MOD stands for modulo operation.
Yes.
Not mod, modulo operation.
Yes, sir.
Modulo operation. It is also written in which language? High level or assembly level?
Assembly level, sir.
Assembly level language. So that is correct, absolutely correct answer. So whenever we are basically going to insert the lexeme div, what we are going to do, look at that. What is my token? My token is basically div. So but my lexeme is div, so I am basically passing div as my first argument, and I am passing the div as my second argument with the help of the insert symbol. Similarly, in case of the mod, I am basically using, look at that, the mod is basically the lexeme, so I am passing it with the help of the insert function as a first argument, first actual argument, and mod becomes my second actual argument, which is basically the token. So lexeme S follows by the token T. I think now it is clear to you. Aditi, is that clear to you? Aditi, are you there? Aditi Ghosh? Aditi, okay. Aditi, is that clear to you? You may reply it via chat box. You may reply it via chat box. If your microphone is not working, Aditi, then I strictly recommend you to arrange a new microphone. Otherwise, it is very difficult for me for taking the Viva. Okay, because it is a part of the question answer session, is a part of continuous assessment. Okay, any subsequent insert fails, or unguarded insert, which basically known as the unguarded insert, okay, fails. Now we are moving into that portions later on. Any subsequent lookup returns the keyword value. Therefore, these cannot be used as an identifier. So naturally, I can able to observe that this div or div, this kind of token div cannot be used as an identifier, because the lookup table, subsequent lookup table, basically lookup table basically returns a keyword value. That's why it cannot be cannot be basically acted as an identifier, because it is sure that in case of the assembly language div is a keyword, in case of the assembly language mod is a keyword. So naturally the lookup function will return negative value. So it is clear to us, or returns the keyword, sorry, not negative value, keyword value. So it natural keyword value or the keyword number of divs. Naturally there are lots of keywords number. For example, in C there are 32 keywords and each keyword has a particular number. Similarly, in assembly level language also there are lots of keywords and each keywords has a proper number. That number has to be returned. If that number is going to be returned, then definitely a keyword value should be returned. That keyword value, if returning by the lookup table, it indicates that div is not an identifier. It's not a variable. Identifier means it's not a variable. mod is not a variable, it's an identifier, because the lookup functions is returning a keyword value. So how to, this is how the keywords may be handled. Next is how to specify tokens. Now my next question is how to specify the tokens. The regular definitions is that let r suffix I be a regular expression. Let r suffix I be the regular expression, where r is the regular expression and I means ith regular expression, and d suffix I be the distinct name. D is the distinct and I is the ith distinct name, represent the ith distinct name. So what happens? Regular definition is a sequence of definitions of the form. D1 produces R1, D2 produces R2. In this way, if we continue, then we can find that Dn produces Rn, where each R suffix I is a regular expression. Okay, well, which over summation union D1 comma D2 comma dot 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 D1 I minus 1. So we are observing that, for example, we have a fax number, suppose, say 91-123-456-7890. So this is a fax number. So summation is basically the, obviously the digit is there, and union with, as said in this particular problem, that that summation union d2 d21 d2 dot 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 di minus 1, where these are distinct, basically the symbols or distinct, basically the variables. So we are observing that basically there are, which symbols are present there? There are hyphen is basically a special symbol. There is a comma is basic, there is a hyphen is basically a special symbol. First opening bracket is special symbol. First bracket, first closing bracket is basically my next special symbol. So digit union, this special symbol constructs my summation basically here. Now we are observing that 9-1, naturally it generates basically the first, this part is naturally generates the country, it indicates the country code. 9-1, for example, indicates the country code of India. So country, that is produces digit plus. Then area, 1, 2, 3. This is represents the area. So it is represented within digit plus, and obviously it is represented within the first brackets. Then exchange digits will be represented by digit plus. So naturally you can see that this is my D1, and I with D1 I produce basically R1. This is my D2 which produce R2. This is my D3 which produce R3. This is my D4 which present R4. This is my D5 which produces R5. So in this way I am basically designing the basically the distinct name, that is D suffix I, and the regular expression, that is R suffix Y. I think now it is clear to you. So look at that, the country will produce the digit, that is R1, then R1 plus. Then we have an area that is produced by the digit plus within first bracket. So this is my area, this is my country, and this is the exchange number that is being represented by the digit plus, and this is the phone number that is represented by digit plus. So what ultimately that we have received, the number is nothing but country, which is 91 here, hyphen, separated by hyphen, then area, followed by the area, then followed by the exchange, then followed by the phone. Okay, this is how we are basically representing. So we are observing that basically it is the summation union D1 comma D2 comma dot 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 di of 1. So naturally I can write it down in this way, that this is my this is my summation, and this is, sorry, this is my D1, this is my D2, this is my D3, and this is my D4. And by combining all of them, we are getting basically the number. Okay, for example, this is basically, this is my whole number and absolute fax number that we have received. Out of that, 91 is my basically the country. Next is 1, 2, 3 is my area. Next one is 4, 5, 6 is my exchange number. Next one is 7890 is my phone number. So in this way I am basically representing it. And with the help of the digit plus, where plus is basically a typical terminal symbol, with the help of that we are basically representing these particular things. I hope that this is clear to you. Another example, let me give it to you. For example, any email. So if there is an email, how the lexemes are basically generated, or how basically the tokens are generated, for how to specify the tokens for an email. Next question is how to specify the token for an email address. For example, xyz.official@company.ac.in. So naturally we observe that big sigma or summation is equal to letter union, then whatever the special symbols that we have two special symbol, @ and concatenation operator or dot. So the letter are XYZ OFFICIAL COMPANY ACIN. These are all letters. It is union by the @ and dot. So letters are how letter, now we need to concentrate on how letters are basically produced. Letters are produced by, look at that, how letters are produced. Letters are produced by small a to small z, or capital A to capital Z. Now how name has been basically produced. So name is basically nothing but XYZ. This is basically your name. So this is produced, this is nothing but multiple letters which is being indicated by letter plus. So name produces letter plus. Next is the address. So how address is basically produced? Very simple. The name, this is my name. Okay, this is my name. Okay, and then followed by the at the rate, which is the special symbol which is here, and then the name, that is the company name, then AC, which is the uh, domain name, and then the country code, that is IN, okay, for India. Okay, so in this way, basically the whole email address is basically generated. So I can say summation is basically produces by basically produces by the name by the name of the employee, or by the name which is represented here by xyz dot official, and then followed by a special symbol at the rate, then followed by basically the company name, dot the domain name, dot the country name, that is in, or stands for India. So this is how we can able to generate basically the email address, generate the token for an email address. Next, now how to generate identifier when identifier is my token. So same thing is there. Letter is basically can be a combinations of small a to small z, or capital A to capital Z. Look at that, every capital or small letters is separated by an or symbol, so that I can able to claim that letter may be a small a, letter may be small b, similarly letter may be capital A, letter may be capital Z. Now digit is also there, digit is separated by digit is separated by, sorry, digit is also there, and digit is separated by 0 or 1 dot 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 up to 9. Identifier is written in this way. First of all, letter should be there, and then letter or digit. This is how the identifier can be written. For example, say num1. How this num1 can be produced? Very simple. So letter within letter or digit whole star. So letter, in case of the letter, I put first of all replaced R. Then I can take a letter here. This letter can also be replaced by letter or letter digit. So this letter I can able to place NUM. So in this way, letter within bracket letter or digit. Next is NUM. This ML can be represented by this, and then letter or digit I can able to choose. I select one. So one concatenation with one. So num1 is generated in this way. So this is how the identifier is generated as a token. Next is unsigned number in C. Unsigned numbers in C is generated by the following distinct rules. Digit is represented by 0 to 9, which all of them are separated by the or symbols. Digits are generic, produces digit plus, okay, where each digit can be basically represented multiple times, or basically replaced multiple times. Next is fraction. Fractions is represented by dot separated by digits, or epsilon or null character, because in case of the fraction, say 10010, there is a dot which is absolutely necessary, and which is followed by either any digit or which may not follow any kind of digit. It may not follow by any kind of digit. I can able to put here a null symbol concatenated. This is basically produce the basically that symbol. So we can write it down in this way. Exponent can also be written and in this way: E, capital E, then plus minus or epsilon digits. Okay. So my plus minus, so plus, let us say plus. Then you have a digit, or it can be represented by, or you have a digit, you have a plus minus or epsilon, either any of you can choose, followed by a particular digit. Say the digit is basically suppose 10. So I have selected out of plus minus epsilon, I have selected suppose plus. So capital E plus 10, that may be basically plus 10, where plus 10 can be represented by 10 to the power 1. Okay, this can be represented, or it can be represented by simple epsilon. Number digit extraction exponent is basically the number. Digit fraction exponent. Digit fraction exponent is basically the our number. So in this way, unsigned numbers in C are represented in tokens. Next, regular expression in specification. Regular expressions in specification. Regular expression describes many useful languages. Regular expressions are only specification, implementation is still required. So given a string small s and a regular expression capital R, does small s belongs to L of R? What is L of R? L of R means the language generated by the regular expression R. What is S? S is basically the lexeme or the string here. So the solution to this problem is the basic of the lexical analyzer. With the help of the lexical analyzer, we can able to solve this problem. What is the problem? A problem is given to us. We have a string given to us, that is small s, and we have a lexical regular expression given to us capital R, and we have to show them whether small s belongs to L of R, or whether small s does not belongs to L of R. So what is the solution of this problem? Solution of this problem, we must use lexical analyzer. However, just the yes or no answer is not sufficient. Whether that means whether S belongs to L of R, yes, or wait, S belongs to L of not belongs to L of R, also no answer. This is not sufficient. So what we need to do? What is our goal? First of all, partitions the input into tokens. That is our goal. So we can able to detect, we can able to generate an algorithm. We can able to write it down in this way. First of all, write the regular expressions for lexeme for each token, which can be represented by two basically production rule. Number produces digit plus, and the identifier is produces by letter within first bracket, letter or digit plus. Okay, so these are the two rules through which regular expression for we can write regular expression for each lexemes of each token. Each lexemes of each token, we can able to write this kind of regular expressions. Construct R. R means regular expression, matching all lexemes of all tokens. So we have to construct a regular expression R, which will combine regular expression R1, R2, and R3, dot, 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 up to Rn. Let input be x1 dot, 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 up to xn. So for all I, where minimum value of I is 1 and maximum value of I is n, we can able to write, we need to check whether the x1 is belongs to L of R, whether the x2 belongs to L of R, x3 belongs to L of R, and xi belongs to L of R. As I said earlier, that whenever you have a language, then you in the language there are multiple strings, and these strings are or inputs are represented by x1, x2, x3 dot 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 xn. Whenever the language is going to accept it, then naturally we can say x1 string belongs to L of R, x2 string must belongs to L of R. If any of the string that is suppose x of k is not belongs to L of R, then we should say that this particular language, this particular string is not belongs to that language L of R. So this language may not be a regular language. Now, if x of 1 dot 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 x of 1 dot 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 x of I belongs to L of R, okay, we can also prove that x1 dot 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 x of I belongs to also x of Rj for some j, smallest for some j. What is j? Smallest such j is the token class of x1 dot 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 up to x of I. Then what we need to do, we need to remove x1 to xi from the input and go to step number 3 once again to generate R or the regular expression, or we can construct the regular expression R which matching the all the lexemes of tokens, all the tokens. Now in the next step, what we need to do, the algorithms gives priority to token listed earlier. Treat if as keyword and not identifier. So we always give priority token to the tokens listed earlier. So if my token is a keyword, then obviously it has given the higher priority. If my token is an identifier, then it has given the lesser priority. So algorithm gives the priority to token listed earlier. How much input is used? And what if x1 to xi belongs to L of R and x1 to xj belongs to L of R? Then what you need to do, you should pick up the longest possible string present in L of R. And then the principle of maximal munch, that is maximal map, is basically possible. Okay. That is longest possible string, pick up the longest possible string in L of R. How much input is going to be used? So we are going to pick up the longest possible string from L of R, and we need to observe that maximum how much is basically accepted from that string. So consider this particular rule, okay, and we are going to follow the algorithms. Say relop is basically my terminal, non-terminal, and relop will produce less than equal to, or greater, or not equal to, or greater equal to, or greater than. This kind of relational operators, or this kind of checking operators is basically used here for considerations. Now id is basically generated by the id is basically my non-terminal here. It generates letter within bracket, either letter or digit whole star. That means simple, basically I can say capital A will produce small a within brackets a or b within bracket whole star. That I can able to say, where small a is letter and small b is digit. Next is the number. Num is equal to digit plus, dot digit plus question mark may be there, and e plus or minus, then question mark will be there, then digit plus, then question mark will be there. So number may be a digit, maybe a number, maybe an exponent, maybe other things also. Delimiter may be the blank space, tab, or new line. These may be the delimiters. Okay. WH or what string is generated by the delimiter plus. Okay. So construct an analyzer that will return token, attribute pairs. So first of all, we are going to construct an analyzer that will return token, attribute as pairs. So first of all, basically there is a less than. We start from this state. There is a greater than sign and greater than sign. If the greater than sign is satisfied, we move from this state to this state. And if there is an equal to sign after greater than, then obviously we move to the final state. Otherwise we go to the final state. Otherwise, if we found only greater than sign, we go to the this kind of state. Similarly, less than, if only less than, then we go to this particular state one. Yeah, then if less than and greater than, then less than and greater than both combined together, that produces not equal to, it goes to final state 2. Next, less than equal to. Less than equal to is another kind of relational operator that we are producing. So we move to state number 3. Next is equal to. Equal to is a lexeme, and it basically denotes that whether this, if this state is basically equal to this state, if left hand side is equal to right hand side, then we are using this. So this is, if this is my initial state, I can, if I get equal to, I can directly move to the final state. Greater than equal to, simple. We start from the final initial state. Greater than means I go to the intermediate state. After that, if I receive equal to, then only I go to the final state. Otherwise I should go to this particular state. Say this is state 5 and this is state 6. So in this way, the transition diagram of relapse has been developed. Or relapse stands for basically relational operators. REL stands for relational, OPS stands for operators. So look at this transitions operators transition diagram. Later, I should stay over there. Then other characters, then I should move over there. Then delimiter, blank space, white space, or new line, etc. Then there is a delimiter over there, I should stay there. And after delimiter, if I found a character or something like that, I can reach to the final state. So this is how the transition diagram can be designed. Similarly, the transition diagram for, this is a transition diagram for identifier, very easily identifier. For example, ID, say 2. So very easily I can decide I should start from Q0, which is my initial state. My letter is basically the ID. Okay, that is my letter. Okay, then I go reach to that particular state. Reach to that particular state, then I produce, suppose, the digit 2. Okay, now I have combined them within the help of the angular bracket. This angular brackets is nothing but other symbols apart from digit and letter. So I naturally ID comma 2, this particularly constructs the whole token. Now whole token has been constructed, means I have reached the final state. Answer. So very simple to understand. Next one is the transition diagram for white space. Transition diagram for white space we have observed, that is delimiter produces by the delimiter, then other symbols will be there. So this is the transition diagram for the white space. Next is transition diagram for the unsigned number. Look at the transition diagram for the unsigned number. We can able to design it in this way. Digit followed by the digit, dot, then digit followed by the digit E plus or minus, then digit, then other. Okay, so this is basically how the real numbers are can be represented. Okay, and this is how the integer unsigned numbers can be represented: digit followed by digits, then others. This is basically the integer number is basically represented. Okay, so digit 1, again digit, say 0, again digit, say 0, then other means say point. After that we have nothing else to do. So at final, we reach the final state we give epsilon, and we can give epsilon, so this can be written as 100. So 100 is nothing but an typical positive integer number. So transition diagram for the unsigned number. Lexemes given to the token must be the longest possible. So for example, assume that my token is 12.34E56. Then starting in the third diagram, I accept the state will be reached to 1, 2. Therefore, matching should be always start with the first transition diagram. If failures occurs in one transition diagram, then extract the forward pointer to the start state and activate the next diagram. If failure occurs in all diagram, then a lexical error has occurred. So let us try whether 12.34E56 is basically generated can be generated with the help of the first transition diagram. So first of all, 1, it is generated, then digit 2 generated, then dot generated, then again digit say 3 generated, then 4 generated, then E generated. After E there is a suppose plus sign, so plus sign is generated, then digit say 5, and then digit say 6, then epsilon we are generating. So what is the ultimate number? Ultimate number is 12.34 E plus 56 epsilon. Epsilon into something gives you, so if something, so 1234 12.34 E plus 56, that will be the correct answer. There is a small mistake over there. There should be a plus present over there, which is missing earlier. If there is, this is not, then it will generate the lexical errors. Okay, so in this particular case, we are observing that token, next token, we are basically calling the next token function. Okay, while 1, that means while true, then switch state. There are several states. Case 10, C is equal to next character, we are calling it, is letter C, then state 10, else if is digit C, then state 10, else state 11, and then break. In this way, we can write a sample code for generating the transition diagram. Very simple. More complex transition diagram for unsigned numbers. So more complex transition diagram is difficult to implement. Am I audible to everyone? Am I audible?
Yeah, yes, sir, audible.
Okay. Thank you. If there is any doubt, please let me know. A more complex transition diagram is difficult to implement and may give rise to error during coding. However, there are ways to better implementation. So you are observing this. This is a more complex transition diagram where multiple things are possible. One to suppose 1, then dot, then I directly go to E, then plus, then then I directly go to E, then plus, I am not using plus, I directly go to that section, that is my digit. So in digit section, say 5, and in digit section I take another loop, say 6 I have taken, and then others, that means epsilon. So 1.E56, that is basically my real number. In this way, the transition diagram may be more complex. input to generator, list of regular expression is priority order. That is the first thing. Lexical analyzer generator, input to the lexical analyze, input to the generator and output to the generator. Two things is needed. Lexical analyzer কোন input গুলোকে নেয় আর কোন output generate করে. First of all, list of regular expression is in priority order. So naturally regular expression according to its priority should be my input to the lexical analyzer. Associated actions for each regular expressions will be needed. That means generate the kind of tokens and other bookkeeping information. What will be the output of the lexical generator? Program that reads input character strings and breaks them that into tokens are basically the outputs of the lexical generator. Reports, suppose we find any unexpected characters or we found any missing characters. Say for example, C is equal to A plus B. So we found that there is a semicolon missing in this particular line. So naturally what happens is that we found that there is a syntactical error. So naturally the reports will generate. So this will be the output. So token specification will be given to the Lex. Then a C code for lexical analyzer will be generated, which is represented by lex.yy.c. Then it will go to the C compiler, then object code generated, then it will give it to the lexical analyzer. Lexical analyzer will take the input program and generate tokens, and token is supplied to the parser. Last slide, how does Lex work? Regular expression describe the language that can be recognized by the finite automata. Then translate each token's regular expression into a non-deterministic finite automata. So first of all, regular expression describe the language. First of all, we generate a finite automata, which regular expressions is basically, which L of R is basically going to recognize or accept. Then what we do, then for each token of regular expression, we are going to design an NFA or NDFA. Then we going to convert an NFA to DFA. We going to convert an DFA to the minimized DFA. Then we emit the code driven by the DFA tables. Okay, so these are basically, then when after the point number 5, we are getting the output, and this output will be the output for the Lex. So this is how the Lex is basically operated. First of all, token specification. So first of all, we give the regular expression to the Lex. Then regular expression or language generated by the regular expression to the Lex. We are giving this as an input. Then this will be converted to a finite automata, mainly non-deterministic finite automata. Then this NFA, then we first of all this L of R, we solve this L of R, we generate the NFA. Then this NFA is derived from the two DFA. Then this DFA is derived into MDFA. Then this NDFA is basically we emit code driven by the DFA tables. So in this way, basically the Lex is going to work. So Lex and Flex, they are very easy to implement but difficult to work, but they are very important because high level languages are very easy, efficient, but difficult to implement. The assembly level language is very efficient, but it is very difficult to implement. High level language is inefficient. Okay, that's why Lex is our only options, Lex or Flex. So this is what we are about to say about this class. Thank you all for joining this class. Hope to see you all in the next week with a new chapter.